Right. Morning. What we want to do is talk about something which is probably of some interest, across the board interest. The issue is that if it is homogeneous, isotropic turbulence, then there is something called Kolmogorov's 5/3 law, which everybody seems to, which seems to have an appeal cutting across disciplines, that there is something called a 5/3 law. And when it is now, this for a long time has been a sort of source of inspiration, in the sense that can one see it, can one, number one question, what does it refer to? It refers to what is called energy spectrum. How is the energy spectrum defined? Well, consider the total kinetic energy associated with the flow. So the total kinetic energy per unit mass, which is that with a factor of half. So that's the total kinetic energy per unit mass, and in Fourier space, which is more convenient for calculational purposes, it is the Fourier transform D3K actually could be a arbitrary dimension over here. In a d-dimensional space, it would be a ddk. And this is something which you can calculate, and you write the definition of what is called the energy spectrum is this total energy. You can calculate in kind of real space, looks very familiar. That's and in Fourier space, just use of identity, and then the definition of this, and it is this E of k which is supposed to go according to Kolmogorov, which uses a certain set of dimensional arguments with some persuasion, and says that it is k to the power minus 5/3 in something which is called inertial range, which is a sort of intermediate range of wave numbers, very small wave numbers corresponding to things where you put energy into the system, and very large wave numbers is where dissipation occurs. Somewhere in between, if this inertial range exists, and it exists if some Reynolds number of the flow, which is velocity times distance scale divided by the kinematic viscosity. If this is much greater than 1, then you are assured of the existence of it. And in this inertial range, you are supposed to see this. Well, I mean, a lot of effort, I mean, across scientific disciplines have gone into this rather spectacular statement. And all right, whether how far and how satisfying is 5/3 and so on are issues which I won't go into, but more or less people are happy with it. Question is, can there be a situation where it is not 5/3? And this is what was the discussion for what this meeting is all about: stratified flows. And stratified flows means that I have a fluid between two boundaries, and there is density so this is, let's say, the z direction, and rho is a function of z because of some constraints that you have put. In the stratified flows, there was a result way back in the late 50s, independently obtained by Bolgiano and Obalhi, which says that E of k proportional to k to the power minus 11 by 5 is a possibility. And a lot of interest, let's say these words like interest and so on have to be taken with a pinch of salt, interest to whom and so on and so forth. Let's not even, I mean, since it's a meeting on stratified flows, let's not get into that. But let's say it is of interest. Question is, will you see it? And independent of the, well, right now, yeah, let's say independent of rho of z. Now, the point is, so there is a lot of effort to see it and so on and so forth. And the issue is, will you see it? Have you seen it? And so on, or under what conditions would you be able to see it? So this is what my purpose is. It should be, I mean, so now the question that was immediately asked at rho of z. Bolgiano and Obalhi did imply that this is to be seen for a stably stratified flow. I mean, this was pretty clearly implied, but the point is that this is something, my number one point in this is that it is important that where to look for, you look for it for stable stratification. Stable stratification is number one, so it has to be a situation which is not top heavy, which is what it is in convection. So stratification of the convective variety should be a problem. So then it is a question of looking at this for stably stratified flow. So I will confine myself to the stable stratification, where here is fluid confined between two plates, T1 and T2, and it is T2 which is greater than T1, and the temperature difference is this. So this is a case of being heated from above, and you have this stable stratification, and so all right. So number one, now mind you, this is also, if you are somebody trying to calculate, actually, the tools are few. It's perturbation theory in various forms. It's, I mean, a stable stratification gives you a starting off ground. If it were the other way around, a convective situation, you wouldn't even know how to get started. One gets started with a stable state where you can define your usual tools and then go ahead and try to see what comes of it. So at least by saying stably stratified, one has some hope, so of being able to calculate. So that's the, now the next constraint. I mean, there has to be, Kolmogorov gave this 5/3 not out of the hat. There was some very specific picture that he had in mind before he could make a statement about this kind of a universal relation. Second question is that do we have this kind of a situation in this particular So all right, one has to write down the governing equations, which I will do for you. So it is Vi dot is equal to Vi dot plus Vj del J. Vi equals minus del Ip, the pressure equation, plus alpha, that's the expansion coefficient. Not worry about the sign, so put a mod sign over here, plus nu del square Vi plus Fi. This assumes, here is the other statement, linear rho z profile. This, now, what's the advantage of the linear profile? I'll show in a minute. Why this is 0, and theta, which is the temperature where, as of the steady state, there is a temperature conduction state which is T1 minus delta T over D times Z. So that's the steady state distribution, and theta is the deviation from the steady state. So del theta del T plus V dot del theta equals minus W. The Z component of this is the diffusion term, lambda del squared theta minus W, plus some forcing, again, which I want to put over here. So that's the, so there is some external forcing at large length scale. You are doing something to stir up the velocity field. Over here, you are doing something to stir up the temperature variable over here. Ultimately, the computation that over the last few years, Mahendra Verma and his various associates have been doing have been with h equal to 0. And my claim would be that putting this in is going to be a great help. All right, so let's, up to this point, now you do some playing around of this total energy, and you will find just a little bit of fooling around would show this answer, that half alpha g delta t theta squared over 2 d3r equals minus integral nu grad v square d3r minus minus alpha g delta t integral grad theta squared d3r plus integral fi vi d3r plus h theta, and there is this alpha g delta t d3. All right, so now this is where, I mean, this for Kolmogorov was also the starting out point, except that he didn't have this, didn't have this, and didn't have this. Wherever I have the Kolmogorov didn't have. And thereafter the argument was that, look, here is a positive definite energy-like quantity. This is a dissipation which is operative at small scales. Here is forcing which is operative at large scales. And if I have a steady state situation where this is 0, so look for a steady state. And steady state would be ensured by whatever is the input and whatever is the dissipation, they get balanced. So you have a picture where there is input at large scales and there is dissipation at very small scales. There is this input is always a constant, so you can go to the limit of nu going to 0 and have the dissipation anomaly, and you have the scale separation between input and output in that range where things are determined only by the input scale, what you are putting in, the rate at which you are forcing the system, that and the local wave number that does that determines everything, and that's what leads to the EK law, E of kk to the power minus 5/3 for Kolmogorov. It's the same in this stable stratification with the linear profile. This would not be so clean if I were to have a nonlinear profile. There would be some addition, a little bit of additions and having to be careful about statements and so on. But linear profile makes it very attractive. The analogy is perfect. Here is a quantity, this total sort of like a kinetic plus potential energy getting dissipated at small scales and getting pumped in at high scales. So the quantity, so there is going to be a flux, which is what Kolmogorov said, that energy flows from high scales to short, large distances to small distances. What flows over here? What flows now is k squared. So you have the identical Kolmogorov argument, but what flows is instead of this to this. It's very clear that if this were not to be, that were to be 0, then you would be seeing this. Question is there going to be a crossover to when this is going to be dominant, and in that crossover dominant situation would this minus 5/3 crossover to minus 11/5. So that is the issue. Question is, are there, I mean, these are you asked whether there are scale invariant solutions. So you carry out this scaling, xi goes to L, xi prime. What am I looking for? Am I looking for something which makes sense? So V therefore goes to V prime L to the power, and there is theta which goes to, that's the extra variable, which goes to L to the power y. So you carry out a scale transformation, ask, is there scale invariance? So am I going to get a scale invariant solution? And you do get, for the scale invariant solution, you must have nu, the kinematic viscosity, go as L, have a scale dependence which is like this, the diffusivity that has a scale dependence which goes like this. This is all very familiar. In Kolmogorov, there is this additional, there is this high dissipation, scale dependent dissipation, which goes like L to the power 4/3. So this is and the expansion coefficient alpha has to have the scale, which is L to the power, this is 1 minus y minus 2z. So 1 minus y minus 2z. All right, so these are the possibilities. Now, y and z, they appear quite arbitrary. So what is it that is going to fix them? They are going to be, now you have this flux. The flux over here, now this flux is, it is going through from high scales to low scales at a constant rate, which is this epsilon, or in this particular case, you can call it something else, I mean, some epsilon bar, but it's going through, and it goes through at a constant rate. And constant rate, and you could have 3 different possibilities over here. You can have that v squared, theta squared, all these are the fluxes, v and theta fluxes scale independent. So that can be scale independent. It can be just theta alone, which is scale independent, and it can be v alone, which is scale independent. How do you test what is the flux for v? Epsilon v, it is v square over t, the rate at which you are pumping it divided by time. Epsilon theta, the rate at which you are putting in the potential energy in the system, which is like this. And So here are the two. You want them to be simultaneously scale invariant. If you want this to be scale invariant and that to be scale invariant at the same time, the scale for this is obviously L to the power 2 minus 3z. The scale for this is L to the power, here is 2y minus z. So you want, number one, both scale invariant, v and theta. Your z is equal to 3 by 2. Your y is equal to z by 2. So z equal, 2 by 3, y equal to z equal to 1 over 3. And this is Kolmogorov. So that's the Kolmogorov situation where so 2 is where I have E theta is scale independent. So Z is equal to 2y. I don't impose scale independence over here. Now in this scale this case over here, your alpha acquires the form is alpha over L to the power 1 minus 1/3, which is L to the power 1/3 or 2/3. So large distance scales, your alpha is falls off, goes off to 0. So essentially, this has become irrelevant variable in the renormalization group sense, and therefore you go to the Kolmogorov fixed point. Now you want this in the next case where it is z equal to 2phi, you are not imposing scale invariance over here. You are imposing this to be scale free, and z is equal to 2y. You want the buoyancy term to be important, and so you impose alpha to be scale invariant, and you have 1 plus y. 1 is equal to y plus 2z, and that's equal to 5y. Or y is equal to 1 over 5, and this corresponds to Bolgiano-Obalhi. So Bolgiano-Obalhi is this. In between, there is another somewhat unphysical thing where epsilon v is scale independent, but epsilon theta can be scale dependent. Over here, in this region, epsilon v falls off as goes like L to the power 4 by 5 in a k space as 1 over k to the power 4 by 5. So this is, and there is a third which is somewhat unphysical, and this in a RG shows up as, so if I do a renormalization group calculation, I have these two, the HH, there are two coupling constants over here, one defined by the FF correlator, which I'm going to put in, D0, and the other the corresponding delta functions, and a 1 over k to the power spatial dimension to keep things which is required by the scale invariance, and HH would have the same structure, but some H0 and the delta functions and so on. D-dimensional space, and you have these two coupling constants. Coupling constants are determined by D0 over some new scale this, and lambda scale, which is some epsilon, which is a way for doing perturbation theory. Never mind right now for this what it is. But you have these two coupling constants, and in this coupling constant, lambda 1, let's say, and lambda 2, you have a fixed point which is over here, a fixed point over here, separated by an unstable fixed point corresponding to this. So here is Kolmogorov, here is Bolgiano, and you want to see what you are going to see is this transfer depending on, I mean, you have to play around with the parameters to see this carefully. So the point, the bottom line is that in this scheme of things, you can do a renormalization group transformation and see that in the presence of this H, it is going to be Bolgiano, seeing Bolgiano would be more straightforward. Now, what if I don't have the H? If I don't have the H, then it is just F. And then as things are a little more tricky, you can arrange yourself in this space where you are going to start away, show departures from Kolmogorov, but flowing to the real fixed point, Bolgiano fixed point would be problematic. That is why, I mean, the computations which Mahendra and his associates carried out saw Bolgiano only over a fleeting range. You could, you started out with this model with this not over there, and it is Kolmogorov as this number remains small, and then Bolgiano would normally have been that push this up very big, make it, but they can't, because if you make this very big, then the point is that the motion will become totally anisotropic. The vertical component of velocity will be essentially killed. After all, this is, I mean, buoyancy force in the a downward direction, and you would be killed by it, and therefore it is very difficult to actually raise this arbitrarily. You have to be careful not to get into a regime where it is all zero flow in this direction and all the flow is, and that happens pretty quickly for them. On the other hand, if you have this H over here, you have the freedom. You pump in a theta, even if this term, I mean, you make this negative, through this pumping in, you are going to get enough velocity into the system so that there is still the possibility of this is not going to become a two-dimensional problem. It will remain three-dimensional, and you will see it. Now, for what would you see with this? I'll be through in a couple of minutes. What can you see for an H equal to 0 and F there? So H equal to 0, and with F, what is the simplest definite thing which you can see? You see Kolmogorov with small values of this. That's definitely true. But it is not going to be Kolmogorov as one of the homogeneous isotropic variety. It is going to be Kolmogorov with an anisotropy. Minutes calculation will convince you that it is all k to the power minus 5/3, but if I'm looking at the v perpendicular square, then it will be one coefficient and k to the power minus 5/3. If it is v parallel square, then it is k minus 5/3, which is this. Now, these are global quantities. These are integrated over. So global quantities are relatively easy to compute. You can calculate it by essentially doing equivalent linearization, keeping things under control, and you can check that there is a difference in the coefficient over here and over here. These coefficients are going to look like, so let me just erase this bit over here and write down that these coefficients which I have, the coefficient of v perpendicular square and d3r and v parallel square of d3r, these coefficients, obviously, if the alpha, the buoyancy is 0, they would be the same, and then it would be 1 plus some alpha 1 times Richardson number. Richardson number is defined from that, and this would be some alpha 2. You start out with a small Ri, you can get a perturbative expansion. It is delta alpha which is alpha minus alpha 1 minus alpha 2, which you can easily calculate. And the calculation has, there is another sort of a relaxation rate which enters with the Richardson number. Therefore, a direct comparison with the simulations of Abhishek and Mahendra is difficult, but you can compare delta alpha in d equal to 3 with delta alpha in d equal to 2, the relaxation rate disappears, and this turns out, if you calculate, roughly about 1/4, which is the same as what they see in the simulations. So at least, I mean, with f equal to 0, if you start looking at, we have, there seems to be some ground for agreement. With h equal to 0, this, as I said, I mean, there is, they have to be very careful to see the Bolgiano. My claim is put in a forcing over here as well, and Bolgiano would be much more easy, much easier to see. There would be a fixed Bolgiano fixed point where you would be flowing automatically for high Richardson number. So that's the, my contribution to this discussion, and we can, any question? Yes, right. No, yeah, right. I mean, here, the point with the difficulty with that is the calculation, this kind of a calculation is going to absolutely fail for the precise calculation would fail. The scaling argument still remains correct, that there should be, I mean, even in RBC, these scaling arguments remain valid, and there should be a way of maybe, that is, Bolgiano is not ruled out by the scaling arguments, but calculationally, it is impossible to tackle within perturbation theory the RBC, because here we start out with a linear theory which makes sense. In RBC, the linear theory does not make sense. So this calculational technique certainly fails over there. And it is, so far as I can see my way through it, there is the scaling argument which would still indicate that it's a possibility. There is the Kolmogorov, this over here where signs are it's negative sign over here, it is a sign flip over here. So the Kolmogorov kind of argument is difficult to push through. That is, you would have to be absolutely sure of which is the dominant flux and so on before you see it. So even if you see it, it would probably be a more rare phenomenon than in the stably stratified case, where I think, I mean, put in it should be.